Okay, welcome to this fourth video in our series on the binomial expansion. Now what we're going to do in this video is we're going to take a relatively simple question really, which is to do the binomial expansion of this, okay, and then use it to evaluate this answer here, 3.9 cubed. Okay, but we're going to do this using both versions of the binomial expansion. Okay, now remember the first version up here is only valid when n, the power, is an integer, a positive integer, and in this case it is. So we can use either of these, and we're going to use them both and compare them. All right, and then we're going to go on to an interesting little problem that we can only solve using the second version down here. All right, so let's do this one first. So we're going to use the first version up here, which you learn about in the first year of A-level or year 11 additional mathematics. Okay, so basically A is going to be 4 and B is going to be negative x, and n is going to be 3. So I've got to make the binomial expansion of that. So I'm going to start by saying that 4 minus x cubed, okay, can be written as, so it's a to the power of n, so it's 4 cubed. The second term is 3c1, okay, which is 3, times 4 squared, okay, times x, which is, or times b, which is minus x. Okay, the next term is 3c2, which is also 3. That's just multiplied by 4 to the power 1, and then it's multiplied by negative x squared. And the final term I would get would be b cubed, and b cubed is negative x cubed. Okay, now I know I could have taken some shortcuts there and simplified that on the way, but it's good practice initially to literally substitute like for like and then work on it step by step. So now I'm going to go through this and say, well, that's 64, okay, plus 3 lots of 4 squared, that's 48, times minus x, so it's going to be minus 48x. So at this point I can write a minus sign there and put minus 48x. The third term is going to be a plus because it's minus x squared, so that's x squared and it's 12, so it's going to be plus 12x squared. Okay, and finally I got minus x cubed because it's an odd power, so it would preserve the minus sign. So that's the simplified binomial expansion of 4 minus x all cubed. Now use it to estimate, or rather to find, the value of 3.9 cubed. So what we're going to do is we're going to put 3.9 cubed, and we're going to use what we've just done and replace the x with 0.1. That's what they're expecting you to do, because 4 minus 0.1 is 3.9. So let's do that, and we've got 64, okay, and it's going to be minus 48 lots of 0.1. Now I am writing it out in full here. I mean, you could of course see that that's going to be negative 4.8 there, but we'll do that on the next line. Then we're going to have plus 12 times 0.1 squared, or 0.01. Okay, so I'm squaring the 0.1 there, and then I'm going to take away 0.1 cubed, which is of course 0.001. Okay, so that is the calculation that I've got to complete, and it will give me 64 take away 4.8, okay, then it's going to be plus 0.12, and it's going to be minus 0.001. Now I can work that through in my head. If I just start with 64, okay, I'll do it sort of cumulatively. So I've got 64, okay, if I take away 4.8, that's going to give me 59.2. Yes, now I'm going to add that onto it, which will give me 59.32. Okay, 59.32. Okay, and finally from that, so if I think of that as 59.320, if I take away this, I'm going to be left with 59.319. Okay, and if you check on your calculator 3.9 cubed, you will indeed get 59.319. all right, now that's exact because the expansion is complete, and that is the answer. Now if we were to do it using this version here, it would take a bit longer actually, because it's not well suited to this problem, but it still works, and I'll show you how it would work. You see, this has to be a 1, it cannot be a 4. So the first thing to do if we're using the alternative, so I'll just put here or, indicating that we're going to look at it a different way. I'm going to say that 4 minus x cubed, okay, can be written as 4 lots of 1 minus x over 4. And you need to be very careful here, because all of that has to be cubed, including the 4 at the front. Okay, now you've got a product there which is cubed, so you can extract the 4 cubed out, so that's the same as 64 lots of 1 minus a quarter x, or x over 4 cubed. Okay, so what we're going to do now is do the binomial expansion of 1 minus x over 4 to the power of 3, and then multiply the whole thing afterwards by 64. So in this case it's quite tedious to do this, but it still works, and I want you to get used to using it because you'll need to in future questions. So it's going to equal, okay, let's just do it down here, 64. Okay, and I tend to now put that 64 outside a huge square bracket. Okay, and it's going to be this 1 plus nx plus nn minus 1 x squared over 2 factorial, and so on. All right, and in this case, when I say x, I mean negative x over 4, because I've got to match this with this. Okay, so it's 1, okay, plus nx, which is 3 lots of minus x over 4. Okay, then it's going to be plus n minus 1 x squared. So when I say x squared, I mean negative x over 4 squared. Okay, and all of that has to be over 2 factorial. Okay, and then the next term is going to be 3 times 2 times 1 times negative x over 4, but this time it's cubed. Okay, and all of that is over 3 factorial. Okay, now at this point I would carry on in this binomial expansion. You keep going, okay, and you keep going until you get to 0, or if n isn't a whole number, you would never get to 0. But as you can see, if I did go to the next term, I would be writing down 3 times 2 times 1 times 0, which means everything that follows would be 0, because every term after that would have a 0 on the numerator. So I can terminate now at this point, because it won't go any further than that. Okay, so I can take that plus sign out, and that is because n is a positive whole number, in this case 3. Okay, so what does that simplify to? Well, I'll leave the 64 there, okay, and a bit of calculating and working out will show you that you've got 1 minus 3/4 of x, okay, and then you've got this thing here, so you've got the 4 squared is the 16, okay, so you've got 16 underneath, the 2 factorial and the 2 will cancel out there, okay, so you're left with 3 over 16, okay, so I've got plus, because it's minus times minus, 3 over 16 of x squared, okay, and the last term, that's going to be a minus term, okay, because it's minus x cubed, and it's going to be a 64. The 3, 2, 1 will cancel with the 3 factorial, which also is 3, 2, 1, so you're just going to be left with 64 minus x cubed over 64, okay, or 1 over 64 x cubed, okay. Now you could at this point multiply each term in the bracket by the 64 outside, okay, so if I go to the next step, in fact if I go up here, from here, so that will give me 64 times 1 minus, now it's 3 lots of 64 over 4, so it's going to be now 64 over 4 of course is 16, so it's going to be 48x. Okay, now hopefully you can see where this is going, because we've had this earlier. The next term, if you multiply 3/16 by 64, that's going to give you 12, and there's our 12x squared, and finally we've got our last term, well the 64 and the 1/64 cancel to give us just minus x cubed, and as you can see that is exactly the same result that we obtained up here when we use the a plus b to the n method. Okay, so if you're careful with your arithmetic, as you need to be in all of these, then it works out nicely. And then we just make the same substitution as we did here, no need for me to go through that again, and I get the same answer, 59.319, as the cube of 3.9. Okay, so just highlight that is the same as this, and you can see that there. Okay, so that was a sort of introduction to using both methods for the same problem. And now we've got this problem that's hidden in the corner here that I'm going to expand, if you'll pardon the pun. I'm going to expand so you can see what's coming next. Now, this is saying, forget the idea that the power is an integer. Here, it's asking us to do the expansion for the square root, and then to use that to find the square root of 3.9. Well, 4 minus x square rooted is the same as doing 4 minus x to the power of a half. And that's what we're going to look at next. And for that, we have to use this version here. Okay, on to the next screen. And this is what we do. So there's the question all set up. And we're going to use this here to find it out what the square root of 3.9 is. And I think you're going to be very surprised at how incredibly accurate this is very quickly. All right, so I'm going to start by saying, what's the expansion for 4 minus x to the power of a half? Now, I need to do what I did before, which is to convert this into the form 1 minus or 1 plus x. This has to be a 1 instead of a 4. So that can be written as 4 lots of 1 minus x over 4. Okay? And all of that, the whole thing, to the power of a half. Okay? And of course, 4 to the power of a half is 2. It's the square root of 4. So that is equal to 2 lots of the expansion of 1 minus x over 4 to the power of a half. Okay? So on the next line, I'm going to write 2, and it's going to be the expansion 1 minus x, where n is a half. So I start in exactly the same way as I did before. 1 plus a half of x. And x, of course, is negative x over 4. Okay? 1 plus nx plus n, which is a half, times n minus 1, which is minus a half, times x squared, so it's negative x over 4 squared. Okay? And all of that is over 2 factorial, or 1 times 2. Okay? I'll just do that as a whole fraction like that, I think, because it makes it easier to follow. Okay, so it's starting to look quite complicated at the moment, and I'll just do one more term, and I should have added something here, and I'll tell you that in a minute. I'm only going to go as far as the term in x cubed. Okay, and you can see what would happen if I tried to carry on. Hopefully, I'll just do this first and then explain. So n minus 1, now I've got to do n minus 2, so it's going to be minus 3 over 2. Okay, then it's going to be the value of x, which of course is x over 4, minus x over 4 cubed, and all of that is going to go over the factorial of 3. In other words, over 1 times 2 times 3, or over 6. Now, if you were to carry on, right, you would not get the 0 term. It would carry on, because you would then have a half, minus 3 halves, minus 5 halves in the next term. You would never get a 0 term. That's because n was not an integer, a positive integer, you see. So for this reason, these expansions do not terminate. Okay, But what we do is we just say plus ... to show that it carries on. Now, what is significant is if x is a small number, in other words, less than 1 or greater than -1, between -1 and 1, as you square it, cube it, and raise it to a higher and higher power, it gets smaller and smaller and smaller. And so these terms become so small that they become insignificant. And you'll see just how important that is in just a minute. So let's just tidy up the expansion by simplifying these terms a bit. So we've got two lots. So you've got here 1 plus, now it's going to be minus x over 8. Then you've got this part here to work out. Well, that will give you, in fact, x squared over 128 minus x squared over 128. Okay, and the final term would be, again, it would be minus x cubed, and if you work all that out, it comes to over 1024. Okay, now if you now multiply everything in there by 2, it gives you 2 minus x over 4 minus x squared over 64 and minus x cubed over 512. Okay, and of course there would be further terms that would carry on after that, but we indicate that like this. But as I said to you earlier, they would become very, very small, because in a minute, you see, we're going to replace x with 0.1, and when we do 0.1 cubed over 512, it's going to be a very small number, you see, and then the term here would be even smaller. So we don't need to even worry about them, and you'll see just why in a moment. Okay, I'll just do the same there to show that that continues. Okay, so now we're going to make a suitable substitution. Now, what I'm going to do is I'm going to do what we did before, and I'm going to substitute x to be 0.1, because we turn the 4 then into 3.9. So so I can now say that the square root of 3.9, okay, now you've got to be careful here. You can no longer say equals, because of course it's never going to be exact. It's going to be approximately equal to, because you're never going to get to the end of this series. 2 minus 0.1 over 4, okay, minus 0.01 over 64, and then it's going to be minus 0.001, okay, over 512. Okay, now if you put into your calculator just the first 3 terms, so we won't even use this one, we'll just look at those 3, okay, and work that out, and that gives us, so I'm just taking this out for the moment, okay, and I'm just looking only at the first 3 terms, and that gives us exactly 1.974843, 1.9748, okay, 974843, okay, and then it goes for 375. Okay, if you got your calculator and put the square root of 3.9 in, okay, square root of 3.9, the actual value on the calculator decimalized to as many decimal places as it gives you is 1.97. Okay, 4843. Okay, and then it starts to deviate. In fact, it's 41766. 41766. Okay, and obviously it continues after that, but that's to quite a few decimal places. Now, if you look at this one, it's already accurate to 5 decimal places just by taking that those first 3 terms. If I included this 4th term as well, all right, so I'm now going to include this 4th term. Okay, so I'm just going to put 3 terms in brackets there. Okay, if you added or subtracted that last term, you get even more accuracy, 1.974843. In fact, no, it's 41797. Okay, 41797. Okay, so instead of ending with 66, it ends in 97. So you've actually got 1, 2, 3, 4, 5, 6, 7 decimal places of accuracy by using just the terms up to and including x cubed. And after that, you see, the 4 term would be so small that it would be only affecting maybe the 9th, 10th, 11th decimal places and so on. So very often with these questions, you only have to go up to maybe the term in x squared, the 3rd term. And sometimes they'll ask you to go up to the term in x cubed, which is the 4th term, as we've done here. Okay, but it's a very interesting insight into how computers and calculators actually work out things like square roots of numbers, because they use this kind of technology and these sorts of algorithms. Okay, so that was an introduction to solving problems and practical applications of the binomial expansion. I hope you found that useful, interesting, and helpful. Take care. Of 1